Everyone to today's University of Texas Energy Symposium for April 8th, 2025. I'm Carrie King, Research Scientist and Assistant Director at the Energy Institute, who sponsors this speaker series. Before I introduce today's speaker more formally, I will point out the upcoming talks for the rest of the semester. Next week, we have Lee Lind, who is a professor at Dartmouth University. He's going to talk about cellulosic biofuels 2.0, or sort of new versions of cellulosic biofuels, and he started companies to produce these new types of biofuels. The week after that, we'll have Sam Porter, founder and CEO of New Ventus, and they work on underground storage and salt caverns for hydrogen and other gases and materials, and to show how that is crucial for thinking about energy transition. Today, it is a pleasure to have Yonghong Chen. She's Chief Scientist at the Grid Planning and Analysis Center at the National Renewable Energy Lab. A little background on Dr. Chen. Research focuses on electricity market design, computation, power systems operations, and transmission planning. Before coming to NREL now for about 2 years, she worked at the Midcontinent ISO, or MISO, for over 20 years and played key roles in the startup and development of MISO energy and ancillary service markets. She holds a PhD in electrical engineering from Washington State and an MBA from Indiana, and she is a fellow of the IEEE. What she's going to speak about today will be the challenges and opportunities in interregional coordination in the areas of interchange transaction, congestion management, reserve sharing, and deliverability across multi-stage operational processes. So this transmission coordination. She will provide an overview of interregional transmission operational coordination project that currently focuses on congestion management, including interregional transmission coordination and real-time operations and operational planning, high voltage DC optimization for intra and interregional services, ancillary service deliverability within and between regions. So with that said, I'm now going to hand it over to Yonghong Chen. As always, feel free to write your questions in the Zoom question and answer feature, and I will interject during her talk as it makes sense. Otherwise, ask them at the end of the talk. And with that said, Yonghong, the floor is yours.
Okay, great. Thank you very much for the introduction, and thank you for this opportunity to share our work on interregional transmission operational coordination. So this project actually started about 18 months ago. That's shortly after I joined the NREL. When I came to NREL, I learned the project. My colleague at NREL worked together with the PNL on the National Transmission Planning Study. So that was a really important project to study the potential transmission expansion across continental US. This study showed a great benefit on building interregional extra high voltage AC and HVDC transmission system to support future system integration. Many of you probably know, currently, in every region, there's a challenging on integrating this future generation into the system. There's a long interconnection queue, and some area like MISO, the grid operator I worked previously started this called the long range transmission expansion, basically to build a transmission system, the backbone to accommodate future system growth. And so this NTP, National Transmission Planning Study, further looking at, how to expand the transmission system across, different regions to provide more benefit. So after I joined, I learned all this great work, and then with my 20 years background working on MISO closely with the control room, on the market design issues. So I, had a great real world experience on this operational side, especially the this kind of things coordination. I brought this up to the NREL team and also DOE. We need to also look at the operational side, because in the planning study normally they just do the global optimization, right? Assume the resource can be optimally dispatched, across very large region, or even across, the multiple region, or even like a continental US. But in reality, the operational side, it doesn't work like that. So you have individual like grid operators or control area. They normally just schedule, within their own footprint. There are some coordination across boundary. So like in ISO, they call it like SIMS coordination. Like for example, between MISO, SPP, or MISO PGM, there are different coordination methods being developed. For example, the coordinated transaction. In some area they also propose like interchange optimization, and then MISO and the PGM actually started this called joint operating agreement, right after MISO started the market, maybe in early 2000. And then this called the market-to-market coordination, really trying to jointly manage congestion across the things. And then in general, if some transmission line is overloaded, the NERC has this called the transmission line loading relief TLR process, really to look at this transaction, which ones have high impact on the transmission flow, and then it may curtail the transaction. But in general, this is probably not a very efficient way, because most of the time you can relieve congestion through redispatch. You don't necessarily need to curtail this transaction. And then there's also this called the reserve sharing group, because sometimes the contingency can be very large. If one region procure reserve to carry this large contingency event, it could be very costly. So even before we had the market, there's a this kind of reserve sharing group formed, like multiple regions can jointly procure contingency reserve to cover some large event. So all these kind of are happening, in the real world, because grid operators, they do understand and see the benefit of coordination. But today, this coordination, in many cases, it mostly happen like in real time when certain for example, transmission violation happened, right? There's very limited coordination in the operational forward process, like in day ahead or intraday. So that's why we feel like there's a great need to also look into the operational side, not only just study the benefit in terms of global optimization, but also given current operational procedure or process, which areas the industry need to look at, in order to bring all the benefits from this transmission expansion. So basically, this project focuses on two areas, basically answering two questions. First, how to improve existing coordination process to enhance reliability and economic efficiency, and then how to coordinate across multiple regions after building these interregional transmission lines, in order to achieve the full benefit. So last June, we had a workshop. It's jointly organized by DOE Grid Department Office and NREL. So we invited grid operators from North America and Europe to share the experience on interregional operational coordination, and also share our scope and the preliminary study on this topic. So if you're interested, you can look online. It's posted on YouTube. And then we also presented a similar topic at the FERC technical conference on like increasing day-ahead real-time market planning efficiency through software. So that was like in June, also maybe at the end of June last year. So if you're interested, you can also look at that. I mean, this presentation, it may give some more detailed discussion. So now we come back to this, coordination problem. So in the US, we've formed some very large ISO RTO. For example, MISO the footprint is, all the way from Canada, Manitoba, all the way to the Gulf. And the PGM also has a large footprint. I mean, the peak load is probably even higher than MISO. So these large scale ISO RTO, they result in significant benefits through the co-optimization on the energy and the reserve scheduling, and also congestion management. On left right side, I have some link to this value proposition study. Like MISO have done this for many years. It can just to work with stakeholder to study, the benefits from this ISO RTO organized, electricity market. It shows like a $4.9 billion annual benefit in 2023. And PGM has done some similar study, and then also show like a $3 to $4 billion benefit from this, organized electricity market, across this large footprint. So, on that share, like the market optimization basically have this kind of system-wide constraint. You optimize them globally. For example, the power balance constraint, it will balance generation and load. Here, just a simplified version. We didn't include losses or interchange, but it's just like a supply demand. We can balance within this large footprint. And then the next thing is like on the transmission constraint, right? So you have the transmission system, you want to make sure the flow will be within limit. So it's also do the redispatch across the large footprint. And then on the reserve side, so we need to procure reserve in the ancillary service market to cover uncertainty. It can come from the forecast uncertainty from load and renewable, and the forecast will never be perfect. And then you need like a regulating reserve, or today they also procure maybe like flexible ramp reserve, to cover this kind of pre-contingency uncertainty. But then if you have some large contingency event, we also need a contingency reserve to cover these. So on large footprint, you can procure reserve, on the most kind of economical resource, and co-optimized with the energy balance. And in recent years, the ISO RTO also noticed like we need to procure reserve at the right location. Otherwise, if you need them, it may be behind the, transmission constraint and cannot be delivered. So, multiple ISO RTOs actually start to implement this called like a post reserve deployment transmission constraint, that can push reserve to the right location. So this is like in general the four bigger system-wide constraints, and within a single ISO RTO, you basically optimize them together, to achieve the global optimization, the benefit. That's why it can bring significant benefit to the footprint, but across the themes, it actually is not as optimal. So this graph is basically showing operations, the control room basically have two major function. One is called the balancing authority. This is really is for these two system-wide constraints. One is the on power balance, basically generation plus interchange, you need to equal to load plus losses. So that in order to achieve that, they may kind of schedule from multi-day ahead, then day ahead trying to figure out which generator need to be committed online. And then, some generator may need multiple day or multiple hours to start. So we need that process to determine what's the most economic commitment from this generation pool. And then when you get into real time, most of the ISO has this 5-minute redispatch. Basically, for generation online generator, you dispatch them, redispatch them based on their cost, and then ultimately, when you get into like a 4-second basis AGC, we're trying to actually deploy reserve to look at the frequency and the actual interchange and the system imbalance, and trying to deploy reserve to achieve this balance. And then so this reserve product procured really to cover the uncertainty, right? When you clear market, you use the forecast data, and then these may not be perfect, and the system condition may change, and this reserve really is be prepared to and then to cover these gaps. So this is on the balancing authority side. So the exogenous variable in this process is a parameter, is kind of like this interchange and then reserve requirement. And then so in terms of interchange, in most cases, it's driven by the scheduled transaction. So the traders can schedule how much to source sync, the transaction from one area, one region to the other. Based on that information, the grid operator will know like what the interchange will be for my scheduling problem. But the traders may not have the perfect information, so sometimes the interchange may be in the wrong direction, right? So it's actually scheduled to send from a high cost area to low cost area. So this is definitely not necessarily the optimal interchange, right? So there's some kind of research work and even some implementation on interchange optimization or coordinated transaction scheduling. But today, like all these ISO RTOs see significant challenges still to achieve like a really optimum scheduling across these regions. So that's kind of MISO also implemented coordinated transaction scheduling. That's like a really multi-year effort to set up the system, like a software and then settlement system or scheduling process in order to achieve that. But then, the other major task is on the reliability coordination. That's really for congestion management. So in this integrated system, especially AC transmission line, the generator, even from outside, the generation and load from outside can also contribute to the flow. So your total flow can have multiple components, the component from your internal energy, basically generation or load. And then the external area can also impact your flow. We call it a loop flow. So the loop flow can come from like external market area, for MISO, maybe from MISO, PGM generation load can impact, this flow, and SPP, or this other market area. But non-market area can also contribute to this flow. So in certain cases, right, just by redispatch your own generator may not be able to fully address the violation. So that's why we have this like a NERC has this TLR, the transmission loading relief process. If for example, MISO figure there is some like a transaction in this non-market area, we can call TLR to curtail this transaction to relieve congestion. But MISO also have this market-to-market coordination process with PGM and SPP. So if they found out, they cannot relieve the congestion, but PGM side may have some generation they can redispatch to address the issue. They can activate this market-to-market coordination process. Then MISO, PGM will add this constraint into their optimization problem and then to redispatch address the problem. But all these need like a separate operational agreement. Like MISO has one with PGM, one with SPP, and then you need to negotiate all these details, like how this market clearing process should work, and how we should do the settlement. So I mean it's just like a very complicated process, and you have to manage with different groups and with different agreement. So you can see all these complexity across teams in today's operation. And then for our project, we basically saying we want to build a framework, a kind of software framework to be able to evaluate all these different possibilities, right? I mean, in addition to all these complexity, we mentioned basically on different constraints, basically tied back to these different system-wide constraints. There's also like a multi-stage process. For example, MISO has this market-to-market coordination with PGM and the SPP, but that's only in real time. There's a very limited coordination day ahead or intraday, and then so you could have like a different coordination possibility, and also this possibility can also be different across different stage. So if you look at this full different system-wide constraint, you could have like a have different agreement, right? Then be able to achieve different things. For example, the C1 is if we only look at the power balance, so that's basically the interchange optimization or coordinated transaction scheduling. That's the work implemented today to address power balance issue. But then this congestion management, like M2M market-to-market joint agreement between MISO PGM and MISO SPP, that's really trying to address the transmission constraint across teams. I mean, it didn't really address the power balance issue. And then when MISO first started the market in 2005, they only have this energy market with power balance and transmission constraints. So at that time, reserve was still managed by individual local balancing authority. So that's another kind of configuration, right? Like you only focus on energy, but reserve will be still managed by individual entity, right? And so you could, well, I mean, the full constraint have 16 possibility, but maybe here like 12 of them kind of make sense. And then the interregional coordination project we're currently working on really focus on the congestion management. It's a C2 and C8. Basically consider either the energy flow is pre-contingency or pre-reserve deployment. And then also look at the post-reserve deployment, with both energy and the reserve considered. But we're kind of building the software framework, give us the flexibility to configure like differently. Mathematically, so there's some kind of simple mathematical formulation on the very first set of constraints fully co-optimized. So that's basically like a individual ISO RTO. You optimize all these system-wide constraints together. So that should give us the most optimal outcome. But on the very right side is basically no coordination at all. So each individual ISO RTO will basically, for example, on the power balance side, from external entity, then they use that in their clearing and then schedule interchange may not the optimal in scheduling. And then on the congestion management, they may have some assumption on the loop flow from external, but it probably never be perfect estimate. And even if they can perfectly estimate what the loop flow from external, I mean, this loop flow kind of the allocation of the transmission capacity may not be the optimal. So it's similar like for reserve, just they look at them just individually. But in the middle is like this coordination method some are implemented today. Like for example, in interchange optimization, the ISO, RTO, these entities may try to optimize the interchange across themes, right? And then really on this market-to-market congestion management, they're trying to kind of share their information. For example, shadow price reflect how the cost of relief the congestion, and then trying to shift that to the cheaper side, or if they cannot address that, they try to let the other side take more control. Basically, it's theoretically on the mathematical side, it's just really trying to figure out what's the best loop flow assumption or allocation, across these different regions. Yeah. So this is basically just like a high level, what the kind of within this optimization problem, what kind of different coordination method are configured. And then, so there's there are kind of two major issues we need to consider, when we study this problem. Like first, as I mentioned earlier, we have this multi-stage operational process, and then you could have like a different coordination method. So that if you look at the combination, it's a lot. And then really we need some kind of framework to not only just perform the simulation study, but also at the end we will be able to have a consistent way to measure the economic and reliability impact, right? Then identify the gaps, which area have the largest gap, and then maybe kind of the industry should work on improving that specific area. So that's one research area, and then the other one is really to look at the trade-off between complexity and how to simplify it. For example, you can do like a global continental optimization, right, in the continental US. I think, for example, in the west US, California ISO has this like energy imbalance market. You basically you can really scheduling together, with external area to achieve more benefit. They don't necessarily need to all join California ISO, but you can maybe just schedule or optimize this scheduling process together. But the things like if you want to do that on a very large scale, there's a computational challenge. And then the question is, is it possible to kind of use some simplified method and then still achieve some great benefit? For example, if you start to build interregional HVDC, how to schedule this HVDC, right? And then perhaps some simplified global coupling can help address that much better. Yeah. So for this IIPO research, we have like three major areas. The first is market-to-market congestion management on these like HVAC lines. So that's basically what's implemented today, like the M2M coordination between MISO PGM and MISO SPP. So really look at the AC high kV AC lines, close to the border, and then trying to figure out how this entity can jointly manage the congestion. So we're having research on how to improve existing coordination method. So that method actually was implemented a long time ago, and then it actually brought a lot of benefit. But the grid operator also, there's some report from grid operator and the independent market monitoring mentioned that some inefficiency in today's approach. Sometimes it may result in some flow oscillation or kind of swing. If the process, I mean, if some of the information is not exchanged quickly and if some generator can move very fast, you may sometimes run into this oscillation issue. And we worked on some potential improvement, on existing method, and also most of the time today we only coordinate across 2 entities, and then if you add maybe 3 entities, some transmission line may be impacted by multiple regions, and if you have coordination across more than 2 entities, that can be much more complicated. And also today there's a very limited coordination in day ahead and intraday, so we're also evaluating what's the benefit and possibility to coordinate in the operational forward process. So that's mostly on this AC transmission system. But then with the building of this HVDC, I mean, there are actually some merchant development is already happening recently, and then several authorities start to really look into this HVDC optimization problem very closely. So this HVDC can be within one region, and it can also be across multiple regions. Sometimes it can be across like multiple synchronized region, like a SPP. Right now, their footprint start to expand to the WEC system, and so there's HVDC across to like a asynchronized interconnection system. So these are very kind of interesting problem to study. And then last one is on the ancillary service side. So not only for energy, we also want to procure ancillary service at the right location. And sometimes, when this ancillary service or reserve product is deployed, it can also impact the interregional transmission flow. And yeah, so I'm also actually previously also had this issue, and but in order to, for example, to also hold a certain transmission capacity to be prepared for some ancillary service deployment, that needs some additional negotiation or discussion with your partner, and also need to implement additional optimization method to achieve that. So this part hasn't been really addressed very well. So we're also studying this. And the next few slides really to give some kind of a small case study we did on this small system. So in terms of like 1A, 1B is really look at the real-time market-to-market coordination problem. So you can have different possibility, like the first one called a benchmark. It's really assume these 2 sides can work like a single entity to optimize the transmission flow together. And but this is only for congestion management, not for power balance. And then the next one is called distributed control. It's really to mimic today's implementation. So the 2 sides can exchange shadow price, and then there one side can estimate how much relief I need from the other side, then through that process to trying to achieve convergence on the price and the flow. And then so it's kind of like a distributed optimization. And then finally, there's one approach proposed by a colleague at ISO New England, basically saying if the 2 sides can exchange the marginal unit and then include them in your clearing, you may be able to achieve faster convergence. So we kind of study these 3 different process, right, within the software. So these kind of show the comparison of these like a distributed and marginal equivalent, compare them to this benchmark. So on this small system, it can both achieve the flow and eventually the shadow price convergence. So both methods can eventually achieve the same result as the benchmark. But if you look at the generation dispatch, this is simulate like a real-time rolling, and then exchanging information along that process and trying to achieve convergence. But today's method, they exchange shuttle price. They know like which side is cheaper or more expensive, but it's really hard for them to know how much cheaper relief the other side can provide, right? So they kind of doing some kind of like a probing, say, oh, I let you take a little bit more control, see what happened, and eventually, hopefully, we can achieve the price convergence. So this is like depending on how much you set in the software process, and then so you need like these multiple step, but through like exchange the marginal unit, you may be able to converge much faster, because if you have the full information about this marginal unit, you know how much it can relieve, right? So this is just some kind of small example to show how we can set up this model to study these different algorithm. And then so in last year's workshop, we also invited a colleague from Europe. So in Europe, they actually have a very different structure. So they actually started like from day ahead, and then recently also implement the intraday. They call it like a market coupling. So they actually couple across the very large, almost like the entire EU scale. So in day ahead intraday, they kind of clear the entire kind of almost like EU scale, so over 900 gigawatt. But they have this zonal model. So the zone is probably most of the time aligned with these countries, and then so of course you can achieve a lot of benefit, right? Just in the day ahead and intraday through this large scale coupling. But because it's a zonal model, when you get into real time, you probably will see a lot of congestion issue within these zones, and even across the region, because the zonal model may not fully represent the physical system. So that still can have a lot of congestion management challenge. But in the US, we have a much more elegant market. We call it nodal market, right? Using this L1P based market design. So it's really in the optimization. We have this security constraint, unit commitment, and economic dispatch. Transmission constraint is basically the physical constraint, with the kind of nodal we call it generation shift factor or PDDF. So this will give us really great and more accurate scheduling, right, within this region. Each of these ISO region can be up to 180 gigawatt. But in the day ahead and the intraday, we kind of discussed really there's very limited coordination across SIMs. And even in real time, we have some level of coordination, but there's a lot of room for improvement. Of course, the US market designer feels like we have much better approach, right, in terms of managing congestion. You achieve the power balance or supply demand balance within these market regions. But across SIMs, in order to achieve similar kind of nodal benefit, it will be actually a lot of challenging, right? First of all, we talked about computational issue, but then you also have this jurisdictional. But Europe has similar kind of jurisdictional challenge, but they have kind of seems to overcome a lot of these, by setting up this market coupling across EU. And then we actually also talked about how to set up this tool or software tool to be able to evaluate these different configuration, right? So like a multi-stage, you go from day ahead or intraday then to real time, and then you can come up with the commitment plan, energy reserve dispatch plan. And then we also kind of implement this thing, we call it emulators, kind of emulation. Basically, at the end, you can plug in the clearing result from different region, and then to kind of mimic like a state estimation, right? You will ultimately see what the flow violation will be, from this clearing result. And then also you have the commitment dispatch cost, from these different regions. And then, if there's a contingency event based on your reserve clearing, we can kind of mimic how reserve will be deployed. And then ultimately we can come up with a total cost then to compare this different structure. So this is like also for this small example, we kind of studied, for example, in day-ahead, if we do like a benchmark, just globally managed congestion, versus like a status quo. But basically, like today, only the owner, the monitor of this line to look at the congestion, but maybe with some very imperfect loop flow assumptions. And then we also kind of study what if we introduce like a simplified coupling, right? We can solve like maybe two areas together with a simplified optimization model, right? For example, LP relaxation. And then we can figure out, for example, HVDC schedule and then transmission allocation. Then we can fit that into this individual ISO clearing. So this is kind of in their head, but the real time we, similar to the one we just mentioned, we can also set up like a different structure. Then you have this together, you will have like maybe 9 different combination. Ultimately, we can look at like a production cost, right? And then the real-time flow violation, and then the total cost, which include the production cost price plus the violation cost. So here, like if you look at like the middle one, like on their head C0, basically their head has no coordination. But then real time you have 3 different ways, like in the very middle is like real time also no coordination. So you will see this, orange bar like at the bottom 7566. That's the highest total cost basically. If you don't do any coordination, you may have lower production cost, but because you don't consider this transmission constraint, but then in real time you run into very high flow violation, and then your total cost actually is high, and then but if we do real time coordination, like the blue bar right next to it, it can result in a little bit kind of lower flow violation, but the production cost will be higher than the scenario you don't consider this transmission. But overall, it will reduce your total cost a little bit to like 7535. But if you look at like on the left side, this set of result is saying if I also do a perfect coordination in their head, then we'll see like actually much more cost reduction, for this small example. And we're at the stage right now, kind of expand this to the entire Eastern interconnection scale. So we have these models, and then we can study, for example, between MISO SPP SIMs. Actually, they post some of the historical constraint with very high settlement cost. So we will try to kind of reflect these constraints, and then to study like all these different combinations, what the outcome will be, and then that can give us very good insight in terms of which area we need to focus on. Yeah. So last, I just want to kind of briefly mention the software system we're building. So NREL has developed this open source software called Sienna. This has been used for this national transmission planning study. So it actually can perform this like production cost simulation. It probably has the largest production cost simulation model ever been studied. So it's kind of across the entire continental US. You can basically study this kind of 8760 production cost simulation. So there's another NREL tool called REES that can do the co-planning of generation expansion and the transmission expansion, looking at like for example future like 20 years with all kinds of policy assumptions and technology cost projection, and then load scenario, and then that one can also iterate with the resource adequacy, basically probabilistic resource adequacy study, and then to identify stress period. But the risk side is more, the transmission is represented on a zonal basis. After you have this like a generation expansion, that can be fit into this translated into nodal model, like Sienna, with some software to identify where this new generation need to be sited, and then looking at the specific year or weather year scenario to study this 8760, and then so before we had this project, within Sienna, it's really just look at optimize the entire system, together, and then so through this project we actually build these kind of operational details. For example, the control area, the area represent the balancing authority, like a MISO or SPP, and then one area actually can split across the multiple synchronized region, and then connected by HVDC, like today I think SPP already has that, and then even MISO also has some connection, HVDC connection, with other part of the synchronized system. And then we also introduced this called the subsystem. It's really to represent this coordinated entity, like for example, MISO SPP can form like a subsystem. Then within this subsystem, we can implement different coordination method. It could be like globally optimized, for congestion, and then or maybe the two sides will exchange information, do this decoupled coordination, and then we have some upcoming project. We're kind of also look into interchange optimization and reserve sharing, and ultimately, this can, Sienna can be easily configured to do multi-stage simulation, and then we can also kind of construct like a different coordination method at different stage. For example, like studying right now, we're looking at, for example, some MISO SPP. If we like today don't do any coordination in real time, in day ahead, but then we coordinate that in real time, versus we also coordinate in day ahead. So all these can be configured, and then ultimately there's a last stage we call the emulator to fit all these final commitment dispatch, into the emulator to kind of mimic the state estimator, to come up with what the final system balance and the flow and even reserve deployment, and then be able to evaluate the total cost and the flow violation. Yeah, so that's all of the presentation. Basically, in summary, we're studying this coordination across multiple regions, after building interregional transmission, and we want to make sure, like on the operational side, we will develop these operations of the future to achieve the full benefit of the transmission system. And NREL is developed this large scale software to be able to study and answer these questions. Yep. So that's all of my presentation. Thank you very much.
Okay, thank you, Yonghong. All right, so ask everyone to submit their questions. I'll start with some here. How much of this problem of coordinating amongst regional transmission organizations is a question of, I don't know, modeling or computational capability to understand the problem? It's kind of what you're in depth in, versus, I don't know, I'll just say maybe non-engineering sort of political or just discussions of, building infrastructure that's shared across one region of customers, and just difficulty in figuring out who pays for the infrastructure. I don't know. Do you have any insights in that from your sort of history of working and working on these problems, seeing difficulty of building, say, transmission across regions and states?
Yeah, so I think today most of the transmission expansion is probably within one region. Even within one region, there are a lot of discussion, to develop all these process, right? In terms of cost allocation, all these kind of studies, and then the interregional can be even more challenging. I think MISO SPP actually started this joint development basically to consider this generation interconnection, that can benefit both regions. So they actually also developed some kind of cost allocation approach, and definitely it will involve probably multi years of effort, just to figure out, who will have the most benefit and how this cost is supposed to be allocated. So certainly, it is a very I mean, maybe huge effort in that area, besides the mathematical side. Yeah.
Right. I mean, how much, I mean, I guess the context of the evolution of the electric grid and how long it's been around for roughly, I don't know, 1.25 centuries. Do you feel like this progress on interregional coordination is too slow, or it's going fast, or it's about the right speed? Just, I mean, to some degree, could we consider these intra-regional coordination problems are just a thing that has occurred in the last 20 years, or how long do you think that these have been a problem worth solving?
Yeah, I think we all know like current process is imperfect. But historically, I mean, it took, like, for example, US took significant effort just to build this ISO RTU structure. I say just by doing that, it's actually already achieved a lot of the benefit, right? Used to be just maybe 20, 30 some balancing authority, right? They just schedule on their own. There's some kind of coordination, but now just consolidate them into large ISO RTU that's already addressed a lot of this coordination issue, right? So you really, one ISO can just optimize them all together. But to even expand that, it is like additional challenge. But I think it's already happening. For example, in the West area, like California, when they start to expand to like with the EIM, like energy imbalance market, and now it's also start to look at the day. So that just show the benefit of this. Like the industry kind of realize that. So it's already happening. But today, with this new development, for example, this HVDC, the merchants already start to build this HVDC across multiple regions. Then really, I think right now all this kind of development is kind of behind that. So you need to start to figure out how to optimally utilize this new transmission, right? So I think basically it's just like historically it is in a good pace trying to address this problem, but today there's a lot of fast development on the transmission expansion side. Then all these other areas need to keep up.
Right. So that's interesting. I mean, and RTO, regional transmission organizations, have been around for what, about in the 30 years or something like this? Or is it a little bit longer? I'm not,
Maybe less. Yeah.
maybe a little less, 20 to 30 years.
Yeah.
So yeah, so we're on that evolutionary path here. And I think you bring up a good point there. You're saying, okay, there are private investors, if you will, trying to build transmission lines across regions, and usually in the case of high voltage direct current lines. And you're saying, yeah, so the challenge is, okay, the RTOs have to actually figure out how to use these. So how do you, I don't know, or what do you know about this? So the private developers they're doing their own calculations and saying, I want to build this transmission line. how do they coordinate with the RTOs, or how much do they have to? And if they build it in some sense independent because they think there's some value proposition, maybe, moving wind, electricity, or solar across long distances. Are they betting that the RTOs know how to use their transmission line? And is their business model sort of at risk if the RTOs don't properly coordinate?
Yeah, this is a great question. I think they, I mean, they definitely start to engage with this stakeholder process, right? Like I know, like for example, MISO in the stakeholder process, this HVDC optimization start to become a hot topic. Um, um, so when in most of the cases, maybe people kind of don't quite fully understand all these operational side challenges, right? So when people do the benefit analysis, they probably will assume like, yeah, you can just schedule them optimally and all that. So yeah, it definitely through all these kind of stakeholder discussion, people probably will understand like both sides better, right? And I think like on ISO RTO side, like they probably when these kind of new facilities in the system, they need to figure out how to manage it. I mean, maybe started with less optimal way, right? Like maybe the owner or whoever is responsible for the scheduling, they will have to determine it outside of the market or have their own ways, right? And it may not be fully optimal, but gradually, I think maybe the industry can gain more experience and then develop more creative ways. But today, there's certainly some gaps, in terms of how to best utilize this new developer.
All right. Yeah, I can imagine somebody is connected with, maybe a power purchase agreement of wind power in one region getting transmitted to another region. But if the RTOs don't coordinate the power flow, then someone's contract sort of becomes a little bit meaningless since if they're not actually connected to the power, or at least even in the right part of the grid. All right. Well, let me ask one, maybe a final question here. And this coordination, sort of the extreme event or extreme contingencies kind of perspective. I mean, Winter Storm Uri, 2021 was sort of, one of the most extreme events that's occurred on the grid, at least in my lifetime that I'm aware of. Maybe not. Well, I guess if there is a contingency and a shortage of generation or reserves, what can you share about how this works in interregional coordination today? Like, if ERCOT, I don't know, well, let's just say south part of MISO needs more power from SPP or another region. Is there always a priority of one region gets to use all its generation resources first, and then if it's got anything else, it may share some with the next region? Or does it get more complicated? Or do you think that kind of prioritization should change, or how is it now, and should it possibly change? If there is coordinated investment in different kinds of infrastructure, would that stay the same, you think?
Yeah, this is also a great question. Like, I mean, can go all the way from planning stage then to the operational basic stage. I think today probably each of these entity will procure their emergency resource. So under this kind of emergency condition, they can deploy this emergency resource, right? So I can see the benefit, like if they start to coordinate or in terms of procure this kind of emergency resource, right? So that's probably potentially one area worth looking at. But when you procure that, there's also a question of whether these can be delivered across the system in terms of like the transmission capacity. And when getting to like a operational time frame, there's like they had basically multi-stage, like for example wind storm Uri, I think several of these grid operator actually they they kind of on the forecasting in their head, right? Because the extreme cold event doesn't happen very often. But when getting to real time, then you could have multiple areas start to see the problem. I know, like multiple grid operator declared emergency, but they're actually still trying to help each other. Like if they kind of have their head clearing, like with scheduling to the other area, even though they have challenging, they're actually still trying to maintain that schedule and then to help each other. But a lot of these coordination when getting to like an emergency condition, how to deploy emergency resource, how to schedule these transactions. These are mostly like through some operational procedures. So definitely not optimized across a larger area. So these can be some area for improvement. I think MISO is probably start to look at how can they deploy this emergency resource within the market optimization instead of just like through some operational procedure.
Okay, very well. Well, thank you again for joining us. This is Yonghong Chen, Chief Scientist at the Grid Planning and Analysis Center at the National Renewable Energy Lab. Thank you for speaking to us at the UT Energy Symposium.
Thank you. Yeah.
All right. Bye-bye.